Hello, my name is Derek Lockhart, and I'm going to talk to you about power beaming. Wireless power transfer supplies electricity without the need for wires. Two categories are near and far field. For near field, power is supplied by magnetic fields using inductive coupling between coils of wire, or by electric fields using capacitive coupling between metal electrodes. Far-field wireless energy transmission, or power beaming, is a technology that has been around for decades, but has become more relevant due to the need for charging of autonomous and unmanned aerial vehicles without landing, and deployment of Internet of Things devices to remote locations on Earth, like a forest, or a massive crop field, or even more remote locations in space or on the moon, where battery replacement or charging isn't possible. Let's start with some history. Going back to 1891, Nikola Tesla demonstrated wireless power transmission with two metal sheets connected to a Tesla coil oscillator, which supplied high voltage alternating current. The oscillating electric field between the sheets ionizes the gas in two Geissler tubes he was holding, causing them to glow. After this, Tesla went all out trying to prove that electricity could be transmitted wirelessly across long distances, but his ideas didn't work and he ended up bankrupt. In the mid-20th century, William Brown is considered by many to be the father of microwave power transmission. Working at Raytheon during World War II, Brown was involved in improving the design of microwave radars. Microwave frequencies range from 300 megahertz to 300 gigahertz. Brown invented the amplitron, which was the first crossed field amplifier. It is a type of vacuum tube that amplifies microwave signals by utilizing an electron beam and resonant cavity. The electron gun emits a focused beam of electrons, which are accelerated by a high voltage. The electron beam passes through the resonant cavity where it interacts with the electromagnetic microwave fields inside, transferring energy to the microwave signal and amplifying it. The modulated electrons in the beam boost the microwave power, which is then extracted for output. This interaction between the electron beam and the cavity's electromagnetic field allow the amplitron to amplify microwave signals to high power. In 1964, Brown demonstrated a helicopter powered by 2.45 gigahertz microwaves. It had a propeller connected to a payload of rectenna elements. Invented by Brown, the rectenna is a specialized receiving antenna that converts electromagnetic energy into DC electricity. A basic rectenna element consists of a dipole antenna with a diode connected across the dipole elements. The diode rectifies the alternating current induced in the antenna by the microwaves to produce DC power, which powers a load connected across the diode. In 1975, a joint effort by Raytheon and NASA's Jet Propulsion Laboratory was led by William Brown and Richard Dickinson and delivered 34 kilowatts from a microwave transmitter to a receiver 1.6 kilometers away. This chart compares that demonstration to recent experiments, with the thickness of the line showing the amount of power transmitted and the length of the line showing the distance power was transmitted. The blue lines are experiments using microwaves and the red lines are those using lasers. Today, researchers are focusing on microwave, millimeter wave, and optical frequencies for power beaming experiments. Microwave frequencies deliver power with the highest efficiency, but they require large antennas. So for smaller applications, millimeter wave or optical links work better. Optical power transmission uses a laser with a tightly confined beam, and receivers are specialized photovoltaic cells designed to convert a single wavelength of light to electric power with high efficiency. Safety is also important. In 2022, Scope M, Safe and Continuous Power Beaming Microwave, used a 10 gigahertz microwave beam to transmit 1.6 kilowatts of power over more than 1 kilometer. According to the principal investigator, Christopher Rodenbeck, who is head of the Advanced Concepts Group of the Naval Research Laboratory, you don't want to use too high a frequency as it can start losing power to the atmosphere. 10 gigahertz is a great choice because the component technology out there is cheap and mature. Even in heavy rainfall, loss of power is less than 5%. The safe part of the name of the project comes from the power density being low enough that there is no danger. Another group, Power Light Technologies, demonstrated that laser power beaming can be safe even when using dangerous high power lasers. Their approach is a virtual enclosure that can sense an object coming near the danger zone and cut power to the beam before any damage occurs. Another research thrust in power beaming is the establishment of a power beaming network using UAVs to transmit wireless power between multiple transmitters and receivers. It is hard to achieve coherence of the multiple received signals, and phase difference of the signals can create mismatch, loss, and decrease in efficiency. Waveform selection and synchronization of the instant wave at the receiver can resolve this issue. The number of transmitters and gain of the power amplifiers needs to be enough to provide continuous power at the receiver. Antennas used for power beaming should have a high gain to reduce path loss and achieve a wide scanning range. Phased array antennas are used for wireless power transfer since they are compact with high gain and have beam steering capability. A tracking and synchronization circuit will keep track of the location of the receiving UAV. The signals must be coordinated at each transmission node so that they arrive in phase at the receiver node. For a UAV power beaming network, microwaves aren't ideal because they need large antennas, so they would use multi-millimeter or optical links. An even bigger idea for the future is space solar power, where a constellation of gigantic satellites in geosynchronous orbit would collect energy with solar arrays and convert gigawatts of power into a microwave beam aimed at receiving antennas on the ground, which would convert the signal to DC electricity. This would be an elliptical rectenna field 6 to 10 kilometers wide that would convert the microwaves into DC power. Additional inverters would then convert the electricity to grid-compatible AC current. In 2022, a team from Caltech was able to test a low Earth orbit satellite that was able to send a small amount of energy to the ground. This was MAPLE, or Microwave Array for Power Transfer Low Orbit Experiment, which is part of Caltech's Space Solar Power Project. MAPLE objectives are to demonstrate beam focusing and steering using SSP-developed CMOS RFICs and flexible antenna arrays in the space environment. MAPLE is contained in a CubeSat frame and weighs approximately 2.6 kilograms. A 32 dipole antenna flexible array radiates microwave energy at 9.884 gigahertz. It uses constructive and destructive interference between individual transmitters in the array to shift the focus and direction of energy without any moving parts. It uses precise timing control elements to focus the power on the desired location by using the coherent addition of electromagnetic waves. Two separate rectenna arrays, about a foot apart, are used to demonstrate the beam steering and focusing capabilities of the transmitting array and processor. An LED is attached to the rectenna and is lit once the beam is converted to DC power, while an attached camera is used to record the evidence. In addition to Maple transmitting to its own receivers, there's a small window through which the array can beam the energy. This transmitted energy was detected by a receiver on the roof of the engineering lab at Caltech. The received signal appeared at the expected time and frequency and had the right frequency shift as predicted based on its travel from orbit. Here are some more proposed ideas for space solar power beaming. The SPS solar power satellite proposed by Thales Alenia Space features nearly 8,000 flexible solar arrays, each 10 meters wide and 80 meters long, which are unfurled from rollout modules and linked together to form two wings. The solar array remains pointed at the sun, so the central transmitter must rotate and also operate with great precision as a phased array antenna to continually steer the beam onto the ground station. The MRSPS, proposed by China Academy of Space Technology, features 50 photovoltaic solar arrays, each 200 meters wide and 600 meters long, which track the sun and send power through rotating high-powered joints and perpendicular trusses to a central microwave conversion and transmission array that points 128,000 antenna modules at the receiving station on Earth. Cassiopeia, proposed by Ian Cash, chief architect of Space Solar Group Holdings, features circular thin-film reflectors that track the sun and bounce light onto a helical array that includes small photovoltaic cells covered by Fresnel lens concentrators, power conversion electronics, and microwave dipole antennas. The omnidirectional antennas must operate in sync to steer the beam as the station rotates relative to Earth. There are major problems with all of these proposals. A 2024 report by NASA says that space solar power will initially cost 12 to 80 times as much as power generated on the ground, and the first power station would require at least $275 billion in capital investment. These are high costs, and there are hard engineering problems, mainly due to the enormity of these satellites and their distance from Earth. Only in geosynchronous orbit can a satellite stay almost continuously connected to a single receiving station on the ground. The systems must beam down their energy at a frequency that passes relatively unimpeded through all kinds of weather and doesn't interfere with critical radio systems on Earth. Unfortunately, most designs call for 2.45 or 5.8 gigahertz within the range used for Wi-Fi. Energy is lost at each step in the conversion, from sunlight to DC electricity, then to microwaves, then back to DC electricity, and finally to a grid-compatible AC current. Efficiency isn't expected to be higher than 11%, so solar arrays and electrical gear needs to be big enough to collect, convert, and distribute around 9 gigawatts of power in space to deliver 1 gigawatt to the grid. A satellite would be hundreds of times larger than the International Space Station. This slide shows how big Cassiopeia would have to be compared to the Burj Khalifa, the tallest skyscraper on Earth, and the International Space Station all the way to the left. No electronic switches, relays, or transformers have been designed or demonstrated for spacecraft that can handle voltages and currents anywhere near the required magnitude.